Okay, can folks see my screen that I'm sharing here? Cool, great.
Yeah.
Okay, so as usual, we're going to start out with a couple quick announcement slides here before we jump into the main topic for today, which is running through a tutorial about how to create custom coadds. So right, today is the 18th of April, 2024, Rubin Science Assembly. So thank you everyone for showing up and arriving on time. So the agenda is basically just these announcements, and then we're going to run through this how to create custom coadds notebook from Data Preview 0.2 on the Rubin Science platform. These science assemblies are only 1 hour, so the plan is that the full hour essentially is taken up with these initial announcements plus running through the tutorial, so no breakouts today. Right, so this is just a generic announcement about RSP accounts, but to get the most out of this tutorial that we're going to go through today, and of course various other activities for DP0 delegates, you would want to fully complete the process of getting your RSP account approved and set up. Other announcements are related to sort of like virtual and or in-person events. So there's the Rubin Community Workshop coming up in July. The call for contributed abstracts is still open, as I understand it, and registration is also open. I can't exactly see everything on my screen because of Zoom, but yeah, so the deadline is June 21st, or when it hits the max capacity of 250 registrants. And then also there's a Rubin Data Academy this summer, these 4 dates during a week in June, starting on June 17th. This is formerly known as DP0 Virtual Summer School, but this is like kind of a virtual intensive series of presentations and hands-on tutorials and co-working sessions for folks to get up to speed on how to use the Rubin Science Platform, RSP, and Data Preview 0 as well. So details of this are now starting to come out, and I believe there was just within the past day or so a new post by Greg from the Rubin Community Science team advertising this Rubin Data Academy 2024. Some other meetings, LSST Europe in September. This should be of interest to all of us, but Rubin's LSSD camera is complete, which is awesome news. That's great to hear, a long time coming from the initial start of construction to now. And then, yeah, Rubin is hiring, and there's this nice short URL that you can go to and check out all the different job openings that Rubin has. So here's just a little bit more about the schedule of upcoming assemblies in this Rubin Science Assembly series. You can go to this website, dp0.lsst.io, for various delegate resources, including this list of assemblies coming up. And so next week at this time, we have sort of a drop-in office hours. That's more informal than what we're going to do today, where we're running through a specific tutorial. And then 2 weeks from now at this time, there's going to be another notebook tutorial on analyzing the point spread function with the LSST science pipelines on the Rubin Science platform. And lastly, I wanted to advertise this portal aspect usability testing that's going on, led by Rubin Community Science team member Andres Fazas Malagón. So there's information on this here, but also in various places, like on on the community forum, if you got the direct message to all DP0 delegates about this. So everyone is encouraged to participate in this and help give feedback on the sort of like the interface and the usability and so forth of the portal aspect of the RSP. Although today we're going to be talking and looking at the notebook aspect, not the portal aspect. So I think that's it for the announcements today. Does anybody have questions about any of that before we delve into the main agenda item, which is going through and running a tutorial on how to create custom coadds? Okay, I'm not hearing any questions, and I don't think that means that my volume is down. So that being said, I think let's try to get started. And so I'm going to try to do this sort of in real time with everyone, starting with actually going into the RSP and getting the right type of image and instance here, because in this case, it's actually important to get the correct version of the LSST science pipeline. So hopefully folks can see that I'm on data.lsst.cloud, and that's where everyone should go in the interest of getting started here. So navigate to data.lsst.cloud. Today we're doing a notebook tutorial, so I'll click on the notebook section. Okay, now this is, ordinarily you might just click through here and not think about it at all, but today this is extremely important. So due to some historical details of when the DP0 data products were actually produced back in 2022, I believe we need to use an appropriate version of the LSST science pipelines in order to work with some of the intermediate data products here. So, perhaps under normal circumstances, you would go to the recommended weekly, but here we actually want to go to an older version. So we go to this scrolling menu and you go down to weekly 2022_40. And then we also want to make sure to choose a large instance here, a large sort of server, if you will, because we're going to use up to about 10 gigabytes of memory at some points in this tutorial. So with that being done, hopefully everyone is following along so far. I'll click start. This can take a couple minutes here because this somewhat older version of the pipelines may not be cached in the same way that the most recent ones are. And so we may have to wait a moment, but that's not such a huge deal. Do I see something in the chat? Okay, I see Bob's question here. So will the code be updated to the recommended weekly version? I guess I can answer that now. The issue isn't so much the code, it's actually the data, and specifically the intermediate data products. So I completely understand the instinct to want to update code to match recent versions, but actually the limiting factor here is the data, not the code. So that's the short answer of it. So anyway, hopefully folks have gotten this far and we see the usual header material in these Rubin Data Preview 0 notebook tutorials. This one is called Construct a Custom Coadded Image. So that's exactly what we plan to do and learn about today. Again, you need to be using this weekly 2022-40 version of the pipeline and a large container size, which hopefully we all got through there just now. And so this first code cell is a good opportunity just to double or triple check that we have the right version of the LSST science pipeline. So let's run this first code cell, which is actually issuing a shell command. And indeed here it says weekly 22_40. You can also see, by the way, hopefully you can see my mouse, but down towards the lower left along the bottom toolbar here, you can also check visually that it says weekly 2022_40. So there's various different ways that you can double and triple check that you have the right version of the pipeline. So yeah, this paragraph here is basically answering the question that Bob just asked about. It's the fact that we need to be compatible with the data products that were generated by now, perhaps a couple of years ago, rather than keeping up with the latest code. So I'm not going to fully read the introduction here, but I'll give sort of like a summary. In my opinion, there are many different cases where one might want to scientifically, for scientific reasons, make custom coadds from the LSST exposures. Maybe later on we can have some discussion about exactly what those different science cases would be, but here we've chosen a specific one to sort of motivate things. But if you have another preferred favorite science case from your own research, you could also choose to think of it in terms of that. So the basic idea that's going on here is that Rubin and LSST, of course, will discover and observe many supernovae. But there's sort of an interesting subtopic of research within the field of supernova research, which is looking to see what we can learn about the progenitors of the supernovae. And so to do that, you could imagine wanting to look at data in LSST in particular ways that happened before or maybe even just before the supernova went off to see if you could see any, say, supernova precursor emission going on there. And you can also imagine reasons why it wouldn't be ideal to just look at this in the single exposures that Rubin produces. For example, this precursor emission, if it exists, could be very faint. And so it's not optimal to just look at, say, the last few single 30-second visits of Rubin right before the supernova went off. You might want to do something more like coadd all the images a month or 2 months before the supernova went off, because then you can go deeper and probe for any fainter precursor emission. And so that's exactly what we're going to do here, is that we have sort of a hypothetical supernova at some specific coordinates. You can see them here. It's like RA of roughly 55.7, DEC of minus 32.3, which of course is in the footprint of data preview 0.2. And it also has sort of a hypothetical date at which the supernova went off, which is given as MJD 60,960, which I believe is something like October of 2025. So note, there's not actually a supernova here, but for our purposes, it doesn't really matter. We just want to sort of give ourselves a hypothetical scientific motivation for why we would want to make coadds at specific times at the specific location on the sky. So there are various caveats for the adopted science use case. Mainly, these are aimed at supernova experts. I'm personally not a big supernova expert, but maybe we have some in the audience here. But anyway, suffice it to say that this is a scientifically legitimate reason that you might want to identify a specific set of exposures within, say, a certain month, and then coadd them to get an image that's deeper than single exposures, but doesn't combine all 10 years of the LSST data. Because if you combined all 10 years of the LSST data, the supernova itself might be rejected as an outlier or contribute in some way, and you'd also have most of your frames that don't have either precursor emission or the supernova. So you're not really sure what you're looking at, but you're probably not looking at the precursor emission in any case if you were to just use like a default 10-year LSST coadd. So as per usual with our tutorial notebooks in the Rubin Science Platform, Data Preview 0.2, we always start with some package imports. We try to collect all our package imports near the beginning of the notebook and then do them once and then use everything later. So here you have a mixture of fairly standard things like NumPy and Matplotlib and pandas that you would use for a wide variety of any scientific analyses of data that you'd be doing in Python. And then you also have some LSST specific imports that come from the LSST science pipelines. And so we'll see exactly what all of these do later, but you have things like the butler, which is the sort of abstracted data interface that allows you to query and write and read data without having to do things like ls on the file system or know what format files are or where they live. So let's run this import. Again, similar to other tutorial notebooks throughout the community science team's materials, we again set some more defaults here right near the top. So these are some like plotting defaults and some pandas defaults about how plots show up and how tables show up if you were to print them out within the tutorial notebook. So let's just go ahead and run these settings for pandas and Matplotlib. Okay, so now we get started with something a little closer to the actual simulated Rubin DP 0.2 data. We need to instantiate a butler object. And again, the butler is this abstracted data interface that allows you to read, write, query all of the LSST data without having to know exactly where files are on a file system or what format they are. So let's instantiate the butler, and we have DP02 in this instantiation call because we want to use the data preview 0.2 repo. Okay, so that ran just fine for me, hopefully for others as well. So now the next major step here is that before we can even make any custom coadds, we want to identify what visits to combine. And by visits, we mean sort of like a single LSST exposure, or perhaps to be a little bit more precise, sort of a combined pair of 15-second snaps. So, but you can, in any case, think of it as a 130-second exposure. So at this sky location, we have something like between 100 and 200 total visits per band in the simulated DP 0.2 data set. And we want to pick the specific ones that correspond to roughly a month before this supernova went off. So to do this, as it says in section 2.1, identify and retrieve the deep coadd. As a matter of terminology here, deep coadd is kind of like the LSST terminology for a standard static sky coadd. And we'll use that throughout this tutorial, even when we're actually talking about our own custom coadd, which is shallower than the original deep coadd that was made by default in data preview 0.2. So to identify the deep coadd, and by the way, we need to identify the deep coadd that exists in the butler already because we need to extract some metadata from it, specifically the list of visits, the complete list of visits from which we will then down select. So we start out here by saying, what's my RA in degrees, what's my dec in degrees, and what's my filter? Here we've chosen I. That's, you could argue with whether that's the best choice for the specific science case, but again, just for the point of illustrating this, we've chosen I band. And then there's a few lines here that are sort of specific to the LSSD pipelines where we're just looking at this notion of a sky map. So this is the way that you tessellate or chop up the sky into pieces in order to make coadds and do data analyses and so forth. So we're going to use the data preview 0.2 sky map, which is indexed by tracts. And then within tracts, there are smaller patches. So the idea here is that we want to retrieve the tract and the patch that correspond to our supernova RA index. So that's what this code is going to do. And then it will print out, I believe, or maybe not print out, but in any case, it will give us what we call our data ID, which uniquely identifies the coadd. Okay, it did print something out. And so this deep coadd is uniquely identified by its band, which we chose to be I band, its tract, and its patch. And here we can see that it turns out that these RA and dec that we chose is in tract 4431 and patch 17 within that tract. Okay, so let's skip some of this optional stuff for now. And let's go on to retrieving the deep coadd input visits. So again, in order to get started here, we need to choose what we're going to coadd. And to do that, we need to get the full list of visits that contributed to the original deep coadd from data preview 0.2. So let's use the deep coadd as an object, and it has some metadata. So you can access that metadata like this to get the inputs. And then the my coadd inputs.visits is the part of the metadata that lists the visits so the exposures that went in here. And if we print out the length, we can see there's 161 total I band exposures that went into this deep coadd. So yeah, in order to now select or down select from there to our specific dates of interest for the coaddition, let's just start by getting a sense of what range of dates are included in this deep coadd to begin with. So to do this, we actually need to sort of match up the metadata that's in the deep coadd with the metadata that's in the broader visit table in order to access the MGDs. So that's what we're doing here. These two lines are going to get the visit table from the butler. I believe it would be also possible to do this through TAP because there's a visits table that you may have seen in the portal aspect, but here we do it through the butler. And then this is sort of the critical line here that matches up the MJDs of your visits that went into the coadd with the visit identifiers. So this is made easier by the fact that this visit table that we just got is indexed by the visit ID. And so that makes it easy to do this with pandas to find the indices that you need and to get the MJDs. So just to double check, we expect that the number of MJDs we retrieved is the same as the number of visits. And indeed, we find 161 MJDs. Okay, so now let's just try to do some actual visualization. I guess it's been perhaps a little bit dry so far with only code and text and nothing to look at, but now we have something to look at. Okay, so let's just take a look at the distribution of times at which, or MJDs, dates, whatever you want to call it, at which these exposures were taken, these 161 exposures. For the purposes of the tutorial, we're also going to define things called window 1 and window 2. So window 1 you can think of as roughly a 30-day window in MJD. That's the month before the supernova went off. And window 2 is kind of like the month before that. So it's 30 days starting 60 days before the supernova went off. So let's just try to visualize the list of MJDs that went into the coadd combined with these notions of the windows, window 1 and window 2 that we defined here. Okay, so Zoom is kind of blocking my screen a little bit, but here we have on the top panel just spanning roughly 4.5, 5 years. So the total span of the data preview 0.2 simulations, you can see that there's a bunch of visits spread over many years, and they kind of seem to bunch up into a set of seasons, which makes sense because you can't see every RA at every time of year at most declinations. And then if we zoom in here, we can look at the sort of 100 days surrounding and before the supernova explosion on MJD 60,960. And so you see we've drawn what window 1 is and what window 2 is, where window 1 is kind of like the month before and window 2 is kind of like the month starting 2 months before. And as it says here, there's 6 visits in window 1 and 10 visits in window 2. So for the purposes of this tutorial, we're going to continue only focusing on window 1. There's an optional exercise for the user at the very end, which is to try to rerun for window 2, but we're not going to get to that today. So let's just do only window 1 for now. Part of the reason for that is that it'll run faster because it has fewer exposures. Okay, so now we're really getting into the heart of this matter of actually creating a custom coad. So the first thing we're going to do is to implement our actual cut on this list, this range of dates that defines what we're calling window 1, the month before the supernova. So we sort of make this Boolean mask and then restrict our list of visits to be where that mask is true. And then we also make this what we call tuple string here that we're going to use for various queries later on, because that's the format accepted by certain functions or methods or calls in the LSSD pipelines. So let's do this, and we can see that we've created our visit string. It has these 6 visits. So these numbers like 919, 515 are the list of simulated visit IDs that correspond to window 1 at the location of the supernova in data preview 0.2. Okay, so that's an important precursor step that we had to do here. Now we're going to get into really the meat of how we're going to use this Butler interface and the LSSD science pipelines to actually run our custom coad. So to start out with, we need to define what's called a collection here. So we want to do this in a standard convention because there's very few, if any, restrictions on where you can write and delete data within data preview 0.2 on the RSP. So we want to be sort of organized about where we put the data and put it under a folder that identifies your username so that you can keep it isolated there and not, say, mess with or delete or have any mishaps with other people's data. So we start out by getting our username because we're going to use that to help define the collection name. That's going to look different for everyone here. And then we're going to also define a collection identifier, which is just this sort of quasi-English string of custom coad window 1 test 1. But basically, we just want to put window 1 and custom coad in here to let ourselves know this is what we were doing during this exercise. So now let's put this all together with the full name of the collection within the DP 0.2 Butler setup. And you can see for me, it's u/a/meisner/custom coad window 1 test 1. You can also now check if this output collection already exists. It may or may not. And if it does, it's not the end of the world. In fact, I'm pretty sure I have many such collections already because I've run this tutorial many, many times by now. So, but in many cases, I suspect you would find nothing, but for me, you'll find a bunch of stuff. This will vary depending on whether or not you've done this tutorial on your own already. I suspect in any case, most folks would have fewer things printed out there than I would. And you can see that there's all these different, basically like timestamp directories is what we call them. So every time you run something within one of these collections, it creates one of these timestamp directories. And so you can see that, okay, I guess apparently on November 26th of 2023, I was running a bunch of tests here. And so you can see there's a bunch of timestamps from then. Okay, so this is great because now we've set up our collection where we're going to actually write our co-added outputs. And then we're actually going to delete this Butler object and make another different Butler object later on. But so delete the Butler for now. Okay, so now we're getting closer to actually running the pipeline. And here we encounter this notion of a simple pipeline executor, which is, you can think of as a class within the LSSD science pipelines that's good for running sort of small jobs managed by the pipeline execution framework of the LSSD pipelines from within a notebook. There are also ways to run this from the command line, but we're not covering that today. So to set up the simple Butler, the sort of simple thing about it is really that it says, okay, we're using DP 0.2, which you can see in the first argument. It defines the inputs, and this 2.2i thing is just the standard place where all the desk DC2 outputs were written. And then you also define the output. So it has DP 0.2 input and output, and for output, we use the collection we just made. So let's run this real quick. So now we have a new Butler object that we're going to use to manage our actual pipeline runs. Then let's see what our collection chain is. So the concept of collection chain is just kind of that Butler will look through a series of different locations to get things when it's running a processing. And so here we should see our output collection first, followed by the sort of standard DP 0.2 output collection. And indeed, we see that. Okay, so now we're at the step where we're actually going to make our pipeline. And here we need to pause, or not pause, but take a moment to explain a little bit about how you define a pipeline, or sort of, what a pipeline is in the LSST Science Pipelines framework. And so the way that the LSST Science Pipelines think of defining a pipeline is it's like a set of tasks basically defined in a YAML file. So YAML is a markup language basically that it's human readable, and you can structure it in certain ways to define like a set of pipeline tasks that get run, like co-addition, source detection, force photometry would be one example of a pipeline you could put together. And so in this case, we're not going to build our own pipeline entirely from scratch. We're not going to write a brand new YAML file. What we're going to do is use this called from URI method. So a URI is a uniform resource identifier, and you can think of it kind of like a URL a little bit with the internet, except it's more general. It could be like a path on a file system, which is something like what we have here. But the way we're going to do this from URI is that we're going to start with the URI of the ZP 0.2 data release production DRP pipeline. And then we're going to isolate specific subtasks within the DP 0.2 DRP pipeline that we want to run, because we don't want to run the whole entire DP 0.2 data release production pipeline. We just want to run a couple things, namely the make warp and assemble coadd. So make warp is something that reprojects the individual reduced exposures onto the tracked coadd geometry. And then assemble coadd is what it sounds like. It takes those warps and just adds them together to make a deeper image than what you get from one exposure or one visit. So let's look at defining what this URI is actually going to be. So here, let's just go to the code, I think is probably the easiest way to do this. But you can see that there's this, in this environment variable, DRP pipe dir, which is inherited from the fact that you're using the LSST pipelines image weekly 2022-40. That DRP testmed1.yaml, that's actually the YAML that defines the entire data release production pipeline that we use for DP 0.2. So if you're ever curious, you could try looking at the whole thing. There's quite a lot there. But fortunately for today, we only want to do these two steps I just mentioned, make warp and assemble coadd. So the URI is just the file name, then you concatenate a hashtag onto that, and then you concatenate make warp, comma, assemble coadd on there. And that is how you define the specific sort of sub-pipeline that we want to run today. So now let's actually build the pipeline. So we're doing pipeline.fromURI. So instead of just having a string that defines the URI, now we have a real pipeline here. In this case, for sort of historical reasons that I won't go into, there's a couple of configuration overrides that you want to do in order to set up your pipeline correctly. Again, I won't go into details, but it is a good illustration of how you would override configurations, because in general, these LSST pipeline tasks, they have huge numbers of different configurable parameters that you could potentially play with or tinker with or optimize for whatever science case you're doing. So the important thing is you have add config override, and then there's the syntax of what task you're looking at is the first argument, and then what parameter you're looking at is the second argument, and then what value you're setting it to is the third argument. So let's do that a couple times without going into the details of what these things actually are in this case. I'm going to skip 3.5 for now, and maybe we can do that while some of this is, or at least discuss it while some of this is running in the background. So let's get on more towards actually running the coadd. So here we just need to define our full query string, which is going to have a major component is the visit tuple string we already defined, but we also want to make sure to put in the tracked and the patch here as well, and note that the sky map is the DC2 sky tessellation. Okay, so that's the query string that we have to send to our pipeline. Otherwise, if you didn't send a query string, it might try to run a big analysis on the whole data preview 0.2, which we definitely don't want to do, especially not in this limited time frame that we have right now. So here is one of the really critical steps. We're defining the simple pipeline executor. And so this brings in the coadd pipeline that we just defined, the query string that we just defined, and the simple butler that we defined, and it actually builds the pipeline. So this is going to take a few minutes because it's doing the actual query of the data to sort of figure out, okay, what are the exact things I need to process here as far as like the inputs especially. And then this is going to take about 3.5 minutes, I think, so we can pause for questions here if I can find, yeah, okay. So this is going to take about 3.5 minutes. Typically, I guess we'll find out if it takes longer because we're all trying to do it at once. So I saw that this started at 9:31 a.m. my time, so let's keep an eye on it. If it goes significantly past 9:35, we may have an issue. But in the meantime, are there any questions to cover here in the next few minutes while we can wait to fill time? I certainly would not be surprised if there's questions. I mean, we've covered a lot of material here so far, and this is some relatively advanced material, getting kind of down into the details of say this Butler interface and also pipelines and tasks within the LSSD pipelines framework. Yeah, I see there's a question about the need to create the simple Butler. So I don't know who all is on here. There may be someone on here who is better qualified to answer this, but I can certainly answer that. And again, to me, it boils down to the collection chaining, right? The first Butler we created was purely meant to look at like retrieving one deep coadd from the data preview 0.2 existing data set, right? That had nothing to do with our output collection. So the need for the simple Butler, in my understanding, is that was where we actually made a Butler that had the notion of our output collection plus the original DP 0.2 Butler with all of its existing outputs and metadata and so forth. Possibly we could have started out this notebook by defining our collection name at the very beginning, and then we only would have needed one Butler. I haven't actually tried that, and that's not currently listed as one of the optional exercises for the user, but it might be an interesting one to try to see if I'm wrong or right about that. But that's my understanding of it. But I believe also formally, if you were to go in and make a new cell and write type parentheses of simple Butler or whatever we named it, I believe it's just a Butler object. So the same as another Butler object. I don't think it's a special class. Like I could be wrong about that, but I think it's just another Butler.
But it's still interacting with the same repo.
Yeah. It just, you've layered on now this output collection that it's going to check for things.
Okay, cool. Thank you.
Because that's, if you didn't have that and then you made these new warp images and then you tried to make a coadd, it might just go back and look at the original warps from DP 0.2, which actually aren't stored because of storage space reasons.
Right, I see.
So it's the sort of layering or the chaining here that matters.
Cool. Thank you.
Okay, it's been about 3 minutes, so now is where we find out if we've overloaded the RSP or not by trying to do this multiple people at once.
Aaron, you had a chart just up above. I was wondering if you could show us that again.
Yeah, I do want to show that to you. I was kind of going to save that for the next thing after this, which was more like 15 minutes under ideal circumstances. But you're always one step ahead of me, Bob. So yeah, let's see if this finishes. We're still within the realm of reason, in my opinion, to see if this runs. Has anybody else's finished, by the way? I don't know. Maybe there's a little bit of randomness in the timing here. Okay, I see at least one other person. Thank you, Melissa, who says theirs is still going. Okay, so we're at about 5 minutes, which is maybe on the 1 sigma long side by now. Yeah, I see a question from Alma. I think it's fine to go ahead, given that we're waiting still.
Yes, thank you. I'm wondering, I guess this can also be done from the command line, not necessarily in the notebook. So is it faster when you do it from the command line, or is it really take the same time and it's recommended to do it from one or the other?
It's about the same. The sequence of steps doesn't look quite the same because in the command line, you don't really make like a butler object on the command line, or you don't really make a simple pipeline executor object on the command line. So the sequence is different, but the amount of time is about the same. And the reason for that is just, fundamentally, you still need to query these data at this stage to you need to query the entire DP 0.2 set of data, which is large. And then at the later stage, you still need to actually like run all the coadds. So there might be a slight difference just because of sort of like the sequence of how you instantiate objects in a notebook, which doesn't have an analog in the command line. But fundamentally, it's about the same. And we actually have a command line version of this tutorial that you could compare it. But my recollection is it's pretty much the same for the reason I said that it's okay. We have someone.
Thanks.
Yeah, it's fundamentally running the same queries and the same reading and writing of data. Okay, we have at least one person who it's finished for, so that's encouraging. However, it's not me that it's finished for. All right, maybe I'm just the unlucky one here. That did take longer than I recalled it doing for, if I was just running this at like a random time of night or something when presumably fewer people are on the RSP. Okay, mine finished. Cool, yeah, thanks everybody. I appreciate the input. So yeah, let's move on now and to actually run the pipeline. So we created just a few cells ago this SPE, simple pipeline executor object that sort of defines our pipeline, its inputs, its outputs, and its YAML definition. So now let's run it. And this normally takes 15 minutes. So I'm slightly concerned that if it takes a little bit longer, that's not good for our timeline here. But let's run this. And then now we can return to Bob's question about the quantum graph or any other questions anyone has. So this is hopefully everyone has started running this. If there are any other questions from the group, I'm happy to take them now because as I said, we probably have 15 minutes to go here under optimal circumstances. Okay, so if there are no questions, then yeah, we can go ahead and look at this, which is kind of a fun thing and an interesting thing, and also a really valuable thing. Especially if you're doing like bigger at scale production runs of the pipeline, the quantum graph is something you definitely want to have a look at to make sure that you understand the sequence of inputs and outputs that happen in a run of the LSST science pipelines. Okay, so yeah, the LSST science pipelines have this notion of a quantum graph, which I appreciate. Maybe from the name, it isn't super obvious exactly what it does, but the quantum graph is just this way of visualizing a pipeline you've defined through this YAML, through the set of tasks and configurations that you've put in place. So quantum graph, it basically gets run. You can see here, we're not going to run this today because other things are running. But there is a command you can run that in Python where you do this pipeline to dot command, and the first argument is your pipeline object, assemble coadd pipeline in our case. And it will produce a graph that looks like this that shows you sort of the flow of your inputs and outputs and what tasks get run. So the way these quantum graphs work is that they always start out at the top. So you read them from top to bottom. And the top is sort of like your very first inputs. In this case, it's what we call the CalExp or process visit images, PVIs. There's different terminologies here. So CalExp are like the calibrated, reduced single exposure or single visit images. And so the reason we start with those is because, nothing about this custom co-addition we're doing needs to go all the way back to the raw data and like process the raw data differently, right? So you can imagine trying to write a pipeline that started from the raw data, and I think that would be possible. But just because there's no need to reprocess the raw data into reduced single visit images, we start with the CalExp. And the other critical thing to know about these quantum graphs is that the nodes, the boxes, have sort of different formatting depending on what they represent. So a light gray box with rounded background, with rounded corners, that represents data. And then a darker box with sharp corners on the rectangle represents pipeline tasks. So you can see here that we start with CalExp, which is just some output data of the reduced single visit images. The CalExp has a bunch of different sub components to it, like it has its world coordinate system, its PSF, and so forth. And then all of that feeds into the make warp. You need the calibrated image and you need its WCS in order to reproject it. And then make warp outputs a couple of different types of warp images, which are then going to be needed to make the final coad. And so the direct warp flows down into, both the different types of warps flow down into assemble coad. And then assemble coad outputs multiple different things, including at the bottom left, there's deep coad, which is the one we're going to look at the most, although there's other types of sort of metadata outputs that also get produced, like this N image, which is kind of like you can think of an integer frame coverage map covering the same footprint as the output deep coad. And so, yeah, I encourage you to, in the future, or if somehow your code finishes before mine, to try running this command, and it'll make one of these files for you. The pipeline to dot name comes from the fact that it originally actually creates an output file with the .dot format, which I believe is from something called GraphViz, which, to be honest, I'm not super familiar with, but maybe some folks on here are much more familiar than I am with it. And then there's this last shell command here, escaped with the exclamation point, where you can convert the dot file into .png file, and that's exactly what's embedded in the notebook here. So, Bob, did that answer the question about what this is? Okay. Are there any other questions? Because I think we still have probably 9 or so minutes, I would guess, under optimal circumstances for this to run. Okay, yeah, James, I think, has hand up.
Yeah, thanks. It's actually more kind of like a general question, but it's a consequence of what you're doing. So clearly what you're doing is you are making a warp, and you're generating a new image, and you're putting that new image into a repository, which means that somewhere you are using disk space. So how much disk space does a user have? Because while I appreciate that disk space is very cheap, it's not infinite. So how does that work on the DP0 system?
Yeah, that's a great question. And they're in the data preview, I believe it's in the data preview 0 documentation, data preview 0.2 documentation, I believe. There's a nice section called something like no parachutes or something, but it basically says in the data preview 0 era RSP, there's very minimal restrictions on things like how much someone could write, or even on whether someone could delete another user's data. So basically, it's just the case that there's very few restrictions right now. And if you get yourself into a bad situation, someone from the RSP team may be contacting you. Personally, I can say I've done things at the kind of like terabyte of output scale on RSP, and I've never had anyone contact me about it. That being said, I'm not sure that's necessarily encouraged for everyone to do. But yeah, hopefully someone is linking. Yeah, thank you, Melissa. That was exactly the website I was thinking of, but you found it faster than me. The answer is there's very few restrictions, and actually we don't want folks trying to delete data now, because that's fairly dangerous with the lack of restrictions. So I think it would be preferred to err on the side of accumulating more outputs rather than trying to meticulously delete things, because deletion right now carries a risk of deleting other people's data, given the lack of safeguards. But yeah, that's a great question. I mean, you are writing files and stuff out. It's not free, as you say.
Yeah, cool. Thank you very much. Thank you.
Yeah, so there is some stuff to look at. So basically, with what we're running now in the background, and hopefully this does finish in time, you can see that the pipeline is printing out a bunch of sort of like, not really debugging information, but just logging information along the way. And so you can see that you're processing various calyx images, which makes sense with what we were looking at in the quantum graph. And you're getting all this information printed out basically about good pixels and PSF matching and so forth. I'm not sure. Yeah, so I can see here it says processing calyx 1 of 5. So let's see if we can see more progress perhaps if we scroll all the way down here. So clearly we're making some progress here. I see processing calyx 2 of 5. I don't know if this is progress at a fast enough rate to actually complete in the time frame I would like this to complete. But we're clearly making progress and getting a bunch of printouts. For me, I seem to have this sort of scrolling through the logging output enabled by default. Or so it seems, but you can also do a control click here to enable scrolling for outputs if for some reason you don't have that enabled by default. That just allows you to sort of scroll through all of this different logging information and watch what's going on in real time. Yeah, I see we're on calyx 3 of 5, so that's definitely progress. I doubt, has anybody else's finished by now, or it's been about 10 minutes. I think it's too fast unless someone was clever and started it before the rest of us. But are there any other questions while we have maybe a few more minutes left before this finishes, ideally? Yeah, I see. Go ahead, James.
Yeah, so it's very much related to what's happening at the moment. So of course the warp step can be parallelized. So is that what is happening here because you selected a large instance, or will it still be trying to do it serial?
Okay, yeah, I mean, this is a good question and a technical question. There may be someone on the call who knows this better than I do, but I will try to answer it. So I don't believe that we did this in parallel here. And to be honest, yeah, that's a good idea. We might consider doing that. The reason we have the large instance is actually because of the memory limitation. So, a fun thing to do would actually be to go and look at top right now. Maybe we can try that because we have the time. And someone can let me know if it finishes, I guess, so that we can get back to it. But if you go to new terminal and you do top, you can see it's using 10 gigs of RAM here. This is our Python, and also 100% CPU. So that's fundamentally, that's the reason why we have the large instance, because you need that amount of RAM. And the other thing that this brings to mind is that if I were to parallelize it, then you would have 4 times, 10 gigs, and then that would be more than the instance accommodates. So I think that's why we aren't doing it parallelized. I'm a little bit more familiar, to be honest, with the command line version of all this stuff. And on the command line, there's a very nice argument when you run the pipeline called -j that allows you to specify the number of CPUs across which it gets parallelized. So the fact that we didn't set the equivalent of -j here anywhere when we were doing this run suggests to me that we're just using the default of running things in serial. But again, you would be using too much memory if you tried to parallelize this. Maybe you could get away with parallelizing it to 2 CPUs here. But that would still exceed the nominal amount of memory on this instance. You can also look at your sort of environment variables that show you, again, what kind of resources you have here. So 4 CPUs and, yeah, only 16 gigs of RAM. So there's not really much room to multiply 10 gigs by a factor of several to gain speed.
Yeah, I see. Cool, thank you.
So let's see what we can find out from this debugging or this logging info, sorry. Has anybody's finished by now? Okay, cool. Thank you, Valerio. So yes, Valerio very smartly started a few minutes before the rest of us and has now had it finish. So I'm not obviously seeing. Yeah, I mean, clearly, it looks to me like I'm in the assemble coadd, the final step, assembling 6 deep coadd warps, essentially. But I don't exactly know how much longer that's going to take. Any other questions while we're here? So maybe I can start out discussing what's next in hopes that I can sort of parallelize that part with what's going on in the background. So the next thing we're going to do after this hopefully finishes in a timely fashion is to look at the quanta. And so as you notice here, we didn't just do SPE.run, we did quanta equals SPE.run. And so the quanta you can just think of as like an object that represents a list of all the things that were done. And then you can very nicely sort of query into it, or not really query, but look at its different attributes and try to understand what happened with the processing. So that's what we're going to do next, is to just loop over the different quanta that are output. This quanta is just a list, and so you loop over it the same way you might ordinarily loop over any list in Python. And we're going to print out the task name, and we should see that 6 of the tasks were the make warp, one for each of the input calibrated exposures, calibrated visits. And then the 7th quanta should be the assemble coadd, which I believe is what's running right now. And then what we're going to do after that is we're going to look specifically at the index 6 in the list of quanta, and that's going to show us more detail about the assemble coadd task, and that's going to help us find the outputs, again, in this way that's consistent with the LSSD pipelines framework, where you're not finding things by LSing around in a file system, but by looking at objects or looking through queries in the butler. Has anybody else's finished, or is it just Valeria who started early? Okay, well, I think I can keep an eye on this through the fact that this has this timer. We can go and just look at a sort of pre-rendered version of the last couple of things here, since we only have 7 minutes, and it seems that this is taking a little bit longer than it would ordinarily with lesser load. Okay, I don't think I actually wanted to look at look at it quite this way. This is an HTML output, but let me stop sharing momentarily and try to find what I was actually looking for here. It appears to me that mine is still running. Okay, so let me reshare my screen. I don't want to share my Zoom screen. Okay, hopefully folks can see my screen again. And let's just go to the executed version of this. Oh, wait, mine finished. Okay, never mind. Wow. I guess I jinxed it sort of by trying to move on. So this finished running. I think it took us slightly longer than normal. So as I said, let's look at the quanta by looping over them first. And you can see, as I said, there's 6 quanta, 0 to 5, for processing all the calyx into warps. And then there's one last one for assembling the warps into the final coadd. So as we can see, the coadd index in this list of quanta is 6. And then let's look at the output for the different coadded products that were made as part of this run. You can see there's various different types. The last one actually is the one we're most interested in, deep coadd, but then there's also some metadata like logs and frame coverage maps and so forth that we won't get into. So if we can index this kind of like a dictionary, and you can see that there's one deep coadd output, which makes sense because we were only running one tracked and patch. That's why there's these square brackets, but only one element within the square brackets. So now let's just look at our final deep coadd, and this is really going to be the end here because the next notebook actually would do things like run custom source detection on your custom coad, but clearly we don't have time for that today. So there's two different options here. Personally, I kind of like option 2 a little bit more, but I'm sure this is just a matter of personal preference. But option 2 essentially just queries by data ID. So we can see here that we have still our collection chain, although now our custom collection also has its timestamp for when I ran this, which makes sense. It's 2024-04-18. And then I'm going to get my new deep coad by simply querying the butler with the data type of deep coad here in the string, the first argument, and data ID of my data ID, which is what we already defined earlier, which is IBAND, and then the track number, which I forget, and I think the patch number was 17, or I can't remember. But anyway, it's the band, patch, and tracked. So now this should work. Yep. Now we've got our new deep coad, and so what we're going to do is simply just take a look at it. So let's just do sort of like the simplest thing and use the LSSG pipelines AFW display functionality to look at our custom coad. And to me, this looks like a co-added image of the sky. I don't know what more to say about it than that. In the next notebook, we get into much more detail, the source detection one, about actually like side by side, how do these look? How does the source detection compare for your custom coad versus the original data preview 0.2 products? And then so lastly, the last thing we're going to do here is just look at our configs to give ourselves a sense that we did change a couple configs, but also understand what other possible outputs we could tinker with in the future. So we just got the config by querying our butler for the make warp config. And then similarly, we can do the same thing to query our butler for the assemble coad config. And sure, let's just go ahead and do this since we have a couple minutes. We can print out all the different configs. So as I said, generally, there are quite a large number of configs, and we could have tinkered with any or many of these if we had wanted to, but we only chose a couple to tinker with, and those were only for sort of historical reasons of code and data compatibility issues. Okay, so we get more into this, especially the source detection in the new image in the next tutorial notebook in the series, data preview 0.29b, custom coad source detection. So I would definitely encourage you to take a look at that. There's also, as I mentioned before, a command line version of all of this. So specifically notebooks 9a and 9b are combined into one command line tutorial. And this is also part of the DP02 documentation, so I encourage you to check that out. And then there's other suggested exercises for the learner. So as I said earlier, we chose this window 1, but we could also choose window 2, which you would want to give it a different collection name, say with window 2 in the name instead of window 1. And then that would be a little bit interesting because it has something like twice as many visits. So you might see how things scale with the number of visits, for example. And then there are other ways you could do the sub-selection of images. So number 2 is suggesting using air math from the visit table and from the deep coad metadata to sub-select visits instead of using MJD as we did here. So we have exactly 0 minutes left, but I suppose if there's a quick question, I could try to take that. Okay, so I'm not seeing or hearing any questions, and I know nobody likes going long on anything, so I think we'll wrap it up there. But yeah, thanks everyone. I really appreciate your patience with some of these steps that took a few minutes to 10 minutes or so, and hopefully there will be another chance where I can come back and show the custom coad source detection notebook and or the command line version in the future. So thank you, everyone. Catch you next time.
Thank you, Aaron. That was really good.
Yeah, thank you, Bob.